of derivative of functions. Since the very definition of derivative involves limit in a rather direct fashion, we expect the rules for derivative to follow closely that of limits. Theorem 5. Let f and g be two functions such that the derivatives are defined in a common domain. Then you can see the following 4 points are similar to those which we had learnt in limits. The only difference is in the third and fourth point, the product and the quotient rule respectively. The proofs of these follow essentially from the analogous theorem for limits. We will not prove these here. As in the case of limits, these theorems tell us how to compute derivative of special type of function. The last two statements in the theorem may be restarted in the following fashion, which aids in the recalling them easily. U into V dash equals to U dash into V plus U into V dash. This is referred to as the product rule. The quotient rule is U divided by V dash equals U dash into V minus U into V dash divided by V square. Let's take an example. Find the derivative of fx equals to x plus 1 divided by x. Solution. Clearly, this function is defined everywhere except at x equals to 0. We use the quotient rule with u equals to x plus 1 and v equals to x. Hence, u dash equals to 1 and v dash equals to 1. Therefore, by using the quotient rule, as shown, the answer comes out to be equal to minus 1 by x square. Write fx equals to 10x equals to u into v, where u is a constant function taking value 10 everywhere and vx equals to x. We know that the derivative of u equals 0. Also, derivative of vx equals to x equals 1. Thus, by the product rule, we have f dash x equals 10x dash whose value comes out to be equal to 10. On similar lines, the derivative of fx equals to x square may be evaluated. We have fx equals to x square equals to x into x, and hence df by dx using product rule equals to 2x. We will get a more generalized view of the above on learning the Theorem 6. So come, let's learn it. Theorem 6. Derivative of fx equals to x to the power n is nx to the power n minus 1 for any positive integer n. Let's see its proof. By definition of derivative function, we have f dash x equals limit h tends to 0, x plus h whole to the power n minus x to the power n divided by h. Now, by using the binomial theorem as shown, we get the result as n into x to the power n minus 1. Alternatively, we may also prove this by induction on n and the product rule as follows. The result is true for n equals 1, which has been proved earlier. We have d by dx of x to the power n. Now, we can write x to the power n as x into x to the power n minus 1. Then, by using the product rule and applying induction hypothesis, we get the final result as n into x to the power n minus 1. Remark that the above theorem is true for all powers of x. That is, n can be any real number. derivative of polynomials and trigonometric functions. We start with the following theorem which tells us the derivative of a polynomial function. Theorem 7. Let fx equals an, x to the power n plus an minus 1, x to the power n minus 1 up to a0 be a polynomial function, where ai are all real numbers and an is not equal to 0. Then the derivative function is given as shown. Proof of this theorem is just putting together part first of theorem 5 and theorem 6. Let's take an example. Find the derivative of fx equals 1 plus x square up to x to the power 50 at x equals to 1. Solution. A direct application of the theorem 6 tells that the derivative of the above function is 1 plus 2x plus 3x square up to 50x to the power 49. Now at x equal to 1, the value of this function come out as 1275. Let's take another example. Solution. Let fx equals 10x. Then, by using the first principle of derivative and writing 10x as sin x by cos x, we get limit h tends to 0, 1 by h into sin x plus h by cos x plus h minus sin x divided by cos x. Then on taking the LCM and then using the formula for sin a plus b, we are remaining with limit h tends to 0, sin h divided by h into limit h tends to 0, 1 by cos of x plus h into cos x. We finally get the answer as sec square x. Compute the derivative of fx equals to sin square x. Solution. We use the Leibniz product rule to evaluate this. Writing sin square x as sin x into sin x. Then using the product rule and simplifying it further, we get the answer as sin 2x.